We're going to start with 9.3 today, which looks at the comparison between arcs and chords. And so there is a number of different relationships that can get a little confusing, but we'll work it out just fine. So first of all, we've got two congruent arcs. And so if two arcs in a circle are congruent, then their corresponding chords are congruent. So do you understand what I mean by that? If you take the two endpoints of the arc and connect them, we get the chord that determines that arc, okay? Or the arc that determines that chord. Notice it says if and only if. What does that mean? This is a subtle point that I think we touched on, but warrants revisiting. The if and only if statement makes it a reversible statement. Okay, so if you have minor arcs that are congruent, their chords are congruent. If their chords are congruent, their minor arcs are congruent. Instead of writing two separate statements, we can lump it all into one statement. Okie doke. Which pairs are congruent? Let's start with the circle all the way to the left. Are those arcs congruent?
Yes.
Why?
Because they were both 50 degrees.
They're both 50 degrees. What about in the two circles in the middle? Are these two 87-degree arcs congruent?
Yes.
How do you know? They actually are not. They could be, but they don't have to be. Why? How do you know that? What's the relationship between those two circles? Let me rephrase my question. Is there any relationship between those two circles?
No.
No. Is there anything in the picture that indicates that those circles are congruent?
No.
No, and if you'll recall in the previous slide, it said that your circles had to be the same circle, like we had here on the left, or congruent circles. And there's nothing in that picture that indicates that those circles are congruent. What about all the way here on the right? Are those arcs congruent? No, obviously they're not. So what we did is I went from the left, which is I went from the left, which is one circle where the arcs have to be congruent, to two questionable circles, to two obvious non-congruent circles. This is a little bit subtle. These arcs could be congruent in the middle, but we don't know that because we don't know the comparison between the circles. In this picture all the way on the right, it's obvious that these arcs are not congruent because it's obvious that those circles are not congruent. They have different radii. What kind of circles are those to the right? Concentric, correct. Concentric sharing the same center, different radius. Okay, so now what we're going to do is take an arc and a chord and draw a radius through it. Or a diameter. The theorem says diameter, but we can use a radius. And this one says that if it forms a right angle with the chord, then it's going to bisect the chord and the arc. In other words, ET is congruent to ES, and the arc TR is congruent to the arc RS. It's not drawn up there, but what kind of triangle is TGS? Tiger, gopher, salamander.
Equilateral.
Nope. Jump.
Right.
Nope. Could be, but we don't necessarily know that it is. Anybody else? Cole?
Isosceles,
Isosceles, why?
because TG and SG are both radii.
Good. Yeah. The segments that aren't drawn in there Those two radii would be congruent, so therefore it has to at least be isosceles. It might be equilateral if we know that TS is equal to GS and GT, but we don't know that. And then, Michelle, we would get right angles here with TEG and GES. And we're going to use that a lot because we're going to be solving the Pythagorean theorem based on those triangles. What's congruent? ET, the segment ET and the segment ES. I think I actually have it here. Hold on. Yeah, there you go. Okay. ET is congruent to ES, and the arc TR is congruent to the arc RS. So when it's perpendicular, it chops both of those things in half. Good? Okay. I think I got a picture for this too. Okay. Same picture. If perpendicular bisector of a chord is a diameter or a radius of the circle. So it's the converse of what we just did. So the other one said, okay, I've got a radius that's perpendicular to the chord, then it's going to cut each of those in half. This one says if I've got a chord and I have the perpendicular bisector must pass through the center of the circle, which makes it a diameter or a radius, depending on how far you want to extend it. So you got a bunch of isosceles triangle things going on there. What about triangle ITS? What can you tell me about that triangle?
That's isosceles too.
Could it be equilateral?
Can be.
It can be, yes. ITS would also be an isosceles triangle. We'll get to that in a little bit. Now, we take two chords and put them in a circle. If they're the same distance away from the center of the circle, then they're congruent, and if they're congruent, they're the same distance away from the center of the circle. And that distance is measured along a perpendicular. Okay, remember bursting of flames run to the river? Months ago we did that.
Will.
Was it Will?
Yeah.
Yeah, so Will burst into flames and ran to the river. You're going to run the shortest path along the perpendicular. That's also how we measured the distance of a chord from the center of the circle. If these two segments are congruent, the chords are congruent. If the chords are congruent, these two segments are congruent. And I know I'm bombarding you with a bunch of theorems, I apologize, but we'll get into some examples in a second where we start doing some calculations. Okay, we good? This problem is going to be given to you in two different formats. Initially, you could see a problem like this, okay, with no picture. Suppose a 10 centimeter chord is 12 centimeters away from the center of the circle. What is the exact circumference of the circle? Okay, that's one. That's the harder one. The easier one would be if I gave you the picture. But you should realize that if I have a 10 centimeter chord, I'm going to have this scenario, and it's 12 centimeters away from the center of the circle. So GE would be 12, TR would be 10. GE is 12, TR is 10. Given that information, what else do we know? Mary?
TE is 5
Beautiful. Why?
because it cuts it in half.
Because
I forget.
that little perpendicular there.
Oh, right.
Which also means what else?
ER is 5.
Good. What piece of information am I looking for, other than obviously the circumference? What do I need to find?
Is it the measure of the angle G? I mean TGR?
TGR. No, that's not what we're looking for. That is a great question, though. We could do that. Paul?
The distance between T and D.
Yeah, also known as the radius. We want to find the radius. So how do I find that radius? Well, let's draw it in there. How do I find GT? You're mumbling. Say it loud, say it proud.
Pythagorean and
Now I understand why you're mumbling.
Yeah.
Pythagorean theorem?
Yeah, something like that.
Yeah, something like that. Good. How long is GT?
X squared.
13.
13. Two ways to find that. 5 squared plus 12 squared is equal to is equal to GT squared, or that's a 5, 12, 13 triangle. That's a common procedure that we're going to do a lot. Take this idea of a radius hitting a chord and create a right triangle, and then solve that right triangle. Okay, now that we know the radius, what we're looking for, circumference. Circumference is equal to 2 pi r, so circumference is equal to 2 times pi times 13, which is 26 pi centimeters. Don't forget units. Approximate answer, you take calculator, multiply 26 times the pi button, and get
81.68.
81.68, thank you. Okay, so there's a couple things to notice here. First of all, the thing that Mary brought up, that these two segments are going to be congruent because it's perpendicular to the chord, therefore it bisects the chord. Second thing is realizing that we're looking for that radius, and we can draw the radius in anywhere. We could do it there, we could do it over here. This is also a radius. You've got a couple different options. You only need one of them because they're all the same. Solve the right triangle, you got the radius, plug and chug, good to go. Problems? Awesome. Okay, in this one it says encircle P. So that little piece of information establishes that P is the center of the circle. We know that EF and GH are both 24. Why is that relevant?
That tells us QP and PR are equal.
Why?
Because this there, like that says, in the circle or the congruent, the two chords are congruent and only if they're equidistant from the center.
Well said. By these two chords being congruent, we know they have to be equidistant from the center of the circle, so these two are equal. Set them equal, solve for x.
I think it was 3.
What is it? 3? Can somebody confirm?
Yeah.
Okay, beautiful. So therefore PQ is
9, right?
9, right? 3 times 4, 12 minus 3, 9. Good. Okay. How about the circumference? Okay, so we know that this is 9, and we know that's 9. Is everybody good on the 9 thing there?
Yeah.
Okay, good. So the chords are congruent, set them equal, solve for x. You get x being 3, plug it back in, you get 9. How do I find the circumference? Show.
So since EF is 24, that means that EQ and QF are congruent and they're both 12.
Well done.
And then you create triangles by connecting E and P and P and F, and then you use Pythagorean.
Either one. Okay, it's a 3, 4, 5 triangle times 3, or you do 9 squared plus 12 squared equals EP squared. And go on and finish it like we did in the last one. The circumference is 2 times pi times r, which is 2 pi times 15, which is 30 pi. And it didn't tell you exact or approximate, so, and we don't have units there, so we'll call it units. And then the approximate answer is, a little help, 90 point something?
94.24.
94.24 units. Okay, good. Problems on that one? Hot diggity. Can I erase? Yeah. Good. All right, that finishes up the first part. All done. What's that?
This was the side for the.
I moved it over here, yeah. I noticed I was spending more time over here, and then I'd always have to walk over there. So I thought I'd try it over on this side and see how it goes. If it doesn't work out, I'll put it over there, or I'll wear it as a belt. Or a tie.
Can you do that?
Yeah, you can pick it up,
Oh, nice.
pick it wherever you want. You could actually cut it into pieces too and put them all over there. I could do like that.
I'll leave.
It doesn't say.
Maybe I won't wear it as a belt. Alright. Let's move on to the next one. Drums today, so it's gonna get a little crazy. 9-4 is exciting. So, when we talked about central angles, I said we're gonna be looking at situations where we take the vertex of the angles and move them all over the place. We've only looked at one scenario, and that's when the vertex is at the center of the circle. What's the relationship between the angle and the arc measure? They're the same, right. So if I have a 76-degree angle, central angle, then the arc is 76. This one is going to look at a different scenario. We're going to move the vertex somewhere else. Okay. We're actually going to move the vertex right there. So what is an inscribed angle? DOG, by the way, is an inscribed angle. What is it?
The vertex of the angle is in the endpoint of the circle.
On the end point of the circle?
No, a point in the circle.
Is a point on the circle. That's it? It's just an angle whose vertex is on the circle. Sure. Agree? Disagree? What do you think? An angle whose vertex is on the circle. Is that an inscribed angle? Probably not. You want to clean up your definition a little bit? What's the difference between the blue and the red? Evan?
Well, the blue one, like, goes through the circle. The other one, the red one, is outside of the circle.
Okay, so how would you change his definition?
An angle made up of two chords with a common endpoint.
Okay, good. Well, no, because what about this? That satisfies your definition, right?
Yeah.
Okay, so how do you tweak your definition so that that doesn't work?
So an angle made up of two chords that share a common endpoint on the circle.
Beautiful. This has the vertex on the circle, we're good to go, except the sides of the angle are not chords. This one has the sides of the angles being chords, but the vertex is not on the circle. You put those two together, and you get an inscribed angle. Vertex is on the circle, the sides of the angle are chords. And this is what we looked at here with all the scenarios that work and don't work. Okay. Here's the one that we want. Here's some of the weird ones that don't work unless we clean up our definition. Okay. Almost exactly what we have up there. Well done. We will actually talk about, this is a type of angle we're going to deal with. This one we don't care about. Looks like bunny ears. And then that one's what we're dealing with today. So if we look at the far left picture, we've talked about angle ADC, which is a central angle, and how it relates to the arc AC. The question is, how does the angle ABC compare to the what's called the intercepted arc AC? What do you think? Equal?
Yeah.
Okay, so therefore you're saying that angle ADC and angle ABC would be congruent because they're both equal to the same value.
ABC and ABC.
Okay, let's do this. If this is 110 degrees, how big is that angle? 110 degrees. That's a central angle, and we know that the central angle is equal to the intercepted arc. How big is angle ABC? And you're arguing it's also 110? No, that's silly. How big do you think it is?
Half of that maybe.
55?
Yeah.
What do you think? That's 55? Or 220, which one? Which way you want to go? Is the angle bigger than the arc or smaller than the arc?
Smaller.
Okay, Emmett?
Are they supplementary?
Ooh, another good guess. So maybe that angle is 70. Anything else? What do you think?
That they're proportional.
That they're proportional to what?
The central angle is proportional to angle ABC.
How would that help me find that angle? What is it proportional to?
Like, ADC is proportional to ABC.
ABC is proportional to ADC.
Yes.
But in order to have a proportion, you have to compare two ratios. So what's your other ratio? I mean, there's 2 dogs to 3 cats. It's fine, but that's a ratio. But if you want to be proportional, you have to compare 2 dogs to 3 cats and 4 graham crackers to 37 moose. You know what I mean? You got to compare 2 ratios. Okay. All right, let's vote. How many think it's 55? Raise your hand. You must vote, by the way. You can't
right.
abstain. How many think it's
is that-
55?
So one of them is right.
One of them is right, yes. No one thinks it's 50. You're not even going to vote for yourself. How many think it's 55? Raise your hand. 1, 2, 3, 4, 5, 6. How many think it's 70? 70 wins. Unfortunately, that's wrong.
What? Emmett.
Blame Emmett. It's actually half the intercepted arc. Okay. So there's the intercepted arc we talked about already. The angle goes and hits 2 spots. So we just have a new terminology for that intercepted arc. And then there's our relationship there. It's half the measure of the intercepted arc. And I got a little demo to show you what that looks like. Okay, so here's a picture. I put B on the circle. I've got an inscribed angle in there. And notice the relationship here. So I measured that angle. The inscribed angle is 21.57. The intercepted arc is 43.15. And then I took the 2 and I divided them and got that ratio of 0.5. If I grab one of these points and change it, these numbers change, but this doesn't change. That doesn't mean that that's not recalculating every time. It is, but the measurement is consistently 1/2. So it doesn't matter what I drag where, that is always going to keep that ratio of 0.5. Okay, and actually notice when I drag B around, nothing changes. Because the intercepted arc doesn't change. And if the intercepted arc doesn't change, then the angle can't change. We'll get to that in a little bit. And again, if I drag that around, the numbers change. Oh, what if I do, ooh. So, oh, it still works, good. All right. Got the idea there?
Yeah.
Beautiful. So that's the second scenario. And when we start doing these calculations, the first thing you're going to ask yourself is, where is the vertex? Is it at the center of the circle or is it on the circle? We have a whole bunch of other opportunities later on to look at different values, but those are the first ones. Okay, so let's start with that. The intercepted arc. Of the intercepted arc. Did I go too fast? You want me to go back?
No.
You got that? Okay. Remember that the angle is always smaller than the arc. Common mistake here is people will tell me that MPQ is 140. What is MPQ?
35.
35. How big is arc PN?
112.
112. Okay. Arc is twice as big as the angle. Angle half as big as the arc. Any problems? Easy? Yeah. Good. All right. How about that one?
Oh, but angle Q is not half of that thing, is it?
Oh, we're not even dealing with angle Q. That's a different scenario completely. That comes later.
Okay.
Now we move the vertex somewhere else. That's even scarier. That vertex isn't even, it's not on the circle or at the center, so you don't want to go there yet. We just focus on angles 1 and 2, because if you try to deal with angle Q, you'll have a meltdown. I don't know if it'd be that bad. How big is angle 1?
34.
34. How big is angle 2?
34.
What do you notice?
They're congruent.
Why?
Because they share the same arc.
Yeah, they share the same arc. So notice it doesn't matter, like in the demo I just did before, it doesn't matter where I drag R. If I bring R over here, it's still going to be 34 degrees. If I bring R over here, it's still 34 degrees because they intersect the same arc. So whatever that arc is, if that vertex stays on the circle, it's got to be equal to the intercepted arc. Make sense? Sorry. Okay. That's what we just did. So two angles intercept the same arc, they must be congruent. I should say two inscribed angles intercept the same arc, they have to be congruent. Because they're half of the same angle. Okay. So more practice of the same thing. The difficulty here is trying to figure out what the heck's going on in the picture. What arc does angle O intercept? Michael? What arc does angle O intercept? Have you lost your voice? Oh, never mind, I won't call on you then. Sorry. I thought you were asking Paul for the answer. But you were using them as your voice box. Completely lost your voice, huh? Don't? We'll take that as a yes. Thank you. Wow, that's brutal. How do you feel? Do you feel sick? You feel great, you just have no voice. Interesting. Emmett?
Aren't the two, isn't angle O congruent to angle R because they intersect the same arc?
Of? Which arc?
FG.
Good. We don't care how big an arc FG is. We care about the fact that they both intercept the same arc. We can find FG eventually, which we'll work towards. But as Emmett said, those two angles intercept the same arc, therefore they have to be congruent. Set them equal, solve for x, what do you get?
5.
5, plug it back in. So if you plug it back in, we know that this angle is 47, and this angle is 47. Therefore, how big is arc FN?
2 times that.
Which is
96.
94, close enough. Okay so far?
Yeah.
CA is a diameter. Therefore, I took B and put it on one of the semicircles. What can you tell me about angle B?
90 degrees.
Who said that?
Oh, no.
Why?
It's at 180.
Good. It's intersecting, or intercepting, I should say, a semicircle, which has a measure of 180 degrees. Therefore, that angle is B. One thing you should recognize that we're going to do a lot of is anytime you have an inscribed angle in a semicircle, it's always equal to 90 degrees.
Is that angle B is 90 degrees?
Yes, that's correct. Which means if I give you a circle, and I don't tell you where the center of the circle is, could you find the center of the circle? This will be part of your homework tonight. Oh, I forgot I moved it over here. Suppose I give you a circle like this. Whoops. And I ask you to find the center of the circle. One of your pieces of homework tonight is going to be to figure out how to find the center of a circle using the stuff we've talked about already. Okay. And if you know, just keep it to yourself. We'll talk about it when I get back on Wednesday. But that's part of the puzzle, how to find the center of the circle. Okay? Rid of that. Come over here. Okay, here we go. This will be fun. A little bit of algebra, a little bit of geometry. How we doing? Not so good? Good?
Fine.
Morgan, let's start with you. What's the relationship between angles 1 and 2? Molly? Close. Ashley? They're complementary. Why?
Because inscribed triangle, or not triangle, yeah, triangle, and a semicircle.
Good. So therefore, how big is angle T?
90.
90. So if angle T is 90, then 1 and 2 have to be complementary, meaning I have to cut that out. So where was I? 1 and 2 are complementary, yes? Add them up, set them equal to 90. What do you get for x? 4. Okay. Then obviously you can plug that in and find the values. What's the relationship between angles 3 and 4 now? Why are they equal?
PQ and RS.
Say again?
PQ and RS.
Yeah, arc PQ and arc RS are congruent, so if the arcs are congruent, their intercepted arcs are congruent. Set these to equal, solve for y, and you get 6, is what he tells me. Is he right? Okay. Plug it back in and find all the angles. And once you know that, you can find virtually every angle in the picture. Well, you can find 1, 2, 3, and 4. Could we find that angle?
No. Not yet.
Yeah,
How? Becca.
you'd have to find the vertical angle to it and then just reducing it.
Yeah, right below it we have a triangle. If you know 4 and 3, you can find that top angle, then take the vertical angle. Can we find angles Q and R? Did you just have a funny thought there, or?
Yeah.
Okay. What arc does angle Q intercept? RS. So therefore, can we find angle Q?
Yes.
Yep. Can we find angle R?
Yes.
Yes. What can you tell me about segment QR and segment PS?
They're parallel.
Proportional.
Why would you say parallel, Paul? Well, there's a lot of P's in that.
Because it's AIA, right? Alternate interior.
It's not actually. Because notice, this angle 4 is going to be congruent to angle Q. In order for them to be parallel, we'd have to know that R and angle 4 are congruent. So we don't necessarily know that they're parallel. They might be, but we don't know that. Okay, we're going to skip that one because it's not really important.